Welcome back. Let's find another transfer function. Just to get familiar with working with transfer functions, working with S's, time domain, frequency domain. All right, so we're given a circuit here, a little bit more complicated circuit than last problem, but still pretty simple. Okay, this is a time domain circuit. V0 of t is the output, and Vi of t is the input. And we've got a 25 kilo ohm resistor here, and we've got a 100 kilo ohm resistor here, and then we've got a 400 nanofarad cap there. And we're asked to find a numeric expression for the transfer function V0 of S over Vi of S. That's part A. And then part B, we want to find the poles, the values that make the transfer function 0 on the denominator. So what we're going to do is we're just going to use node voltage in the Laplace domain. So I'll redraw the circuit here with some variables because we don't want to be dealing with these constant values. It's ugly, ugly, ugly. So we'll redraw this guy in Laplace domain. So this becomes V0 and it's a function of S. And this over becomes big Vi and it's a function of S. And let's just call this resistor R1. The 25 kilo ohm, we'll call it R1, and the 100 kilo ohm, we'll call that R2. The cap, we'll use the frequency domain, Laplace domain value for impedance 1 over SC. Call this node A at the top. So this is also node A, and it has voltage. It has voltage V0 at the top because we're rising. This is also node A over here, right? And this is the ground. So it's 0 volts here, so 0 volts here, rising up V0. There's V0 volts here, so it's V0 all the way across where the A is, all at node A. These 3 dots, it's all one node. All right, then we need to choose some reference directions, right? So we'll say this is going in, the current. We'll say this is coming out of node A, and we'll say this is coming out of node A. There's nothing in here because it's just node A, right? Just kind of a review of node voltage method. So we're doing node voltage. So I like to get calibrated by reminding myself that in is negative and out is positive. In is positive and out is negative. And what we're doing is we're summing V over Z terms, currents by Ohm's law, or V over Z. So the equation, the node voltage equation. So this so this node here is Vi voltage. This is V0. So this current's going to be Vi minus V0 over R1. So it's going to be Vi minus V0 over R1. That's this current. This current coming down here is just going to be V0 over R2, and it's minus because it's leaving. This current leaving node A here is going to be V0 over 1 over SC. Those sum to 0. Okay, then we just solve for V0 over Vi, and we'll have our transfer function. That's it. So let's see, multiply this term out, Vi over R1 equals, and then move the V0 terms over and factor out all of this commonality stuff. So it's SC plus 1 over R1 plus 1 over R2. Right, just by rearranging and factoring out the constants, and then we can solve for V0 over Vi. Now it's just going to be 1 over R1 times 1 over SC plus 1 over R1 plus 1 over R2. And that's right. It's a little bit confusing. Good to stop and check. But what we need this in this partial fraction form where it's S plus box, something over S plus box. Okay, so we have this this SC. We need to get S by itself. So let's do that. So let's pull the 1 over R into the numerator, 1 over R1, and the denominator is going to be SC plus 1 over R1 plus 1 over R2. And then if you multiply, we want to get rid of this C. So if you multiply the top and the bottom times 1 over C, okay, that'll get rid of the C here and put it in the form that we seek, this partial fraction form C. We want it in this form here because we have these inverse Laplace transforms to take stuff apart. And also we can look at the poles and say some stuff about the transient and the steady state response. That's why we're doing this stuff. So this is going to be 1 over R1C over S plus 1 over R1C plus 1 over R2C. Yeah. Then these are constants. And so 1 over R1C is 1 over 25 times 10 to the third R1. C is 400 times 10 to the minus ninth. 400 nanofarad is 100. And 1 over R2C is 1 over 25 times 10 to the 3, 100. This R2 is this guy here, 100 kilo ohm, and then 400 times 10 to the minus 9, it's going to be 25. So we can plug these in here, here, and here, and running out of room, but got barely enough room to finish this thing. So the transfer function, h of s, which was defined as in the problem, as these two, ratio of these two signals, right? Because the transfer function could be the ratio of any two signals. It's just those signals are just chosen, really. Here we're using these two voltage signals, but they could be any signals. Anyway, yeah, V0 over V. So that's all this thing. So this is just, it's just 100 over S plus 100 plus 25. This one's 100. This one's 25. So it's 125. That's the numeric expression. That's the answer to part A. And the pole, S equals minus 125. That will make the denominator 0. That's the answer to part B. Okay? Just some fun dealing with the S's. Algebra.